let's talk about descriptive statistics. So the first part of this is on central tendency. The second part is on variability. This is stuff you've seen in your prereq course. I'm fairly certain in like 140 or whatever version of that course you took at a different university or something like that. But this is sort of the main meat and potatoes of those courses. I just want to review quickly about what those things are, just so we're talking about the same thing, especially as it comes to variability. So descriptives. So once we have a distribution, we want to go beyond just the shape of the distribution, describing, oh, okay, it looks like it's normal, it looks like it's skewed, it looks like it's all kinds of different words for describing distributions. We actually want to be able to summarize it. Right? We want to be able to say, okay, well, what's the most common or the central value or the most frequent value that represents this distribution? And in that, we're talking about the sort of central tendency, right? The averages, and I use the term averages almost like with air quotes, the average, because the way we use average differs depending on what kind of data we're dealing with. But we use the term average to mean all of these different things all the time, which is why the word becomes a little bit confusing. But also, in addition to wanting to know what is the most common or typical value look like, I want to know, well, how far do scores differ from that typical value? How much do they vary from each other? Is there a lot of variability? Are they very heterogeneous from one another? Are they very homogeneous and very, very like one another and very similar? Very, that's what I'm looking for. Almost like carbon copy clones, all super close together. Right? So those are the two things. This is sort of the central tendency. This is the spread of the distribution of the variability. So those are the two things we want to know about any distribution if we're trying to sort of understand it. All right, so typical value looks like. All right, so what does a typical score like in the distribution? Well, you got the mode, the median, and the mean. It's like, you know, I'm sure you've seen before. You guys, a little cartoon. This is like my girlfriend thinks I'm mean, and my current one thinks I'm average. Maybe you set your bar too high. If this one, it says, add the numbers, divide by how many numbers you've added, and there you have it, the average amount of minutes you sleep in class each day. And then here, on average, when people say average, they mean mean. When I say average, I mean mediocre. I'm somewhere in the middle. So there are all these different ways in which the words can be a little bit confusing and be used to mean different things, and people often will confuse them. The term average really is referring to the mean, the arithmetic or mathematical average, but we tend to use the word average to mean the mode or to mean the median as well, and that's why the term average can be kind of confusing. So this is a sort of quick way of, this is like almost like a crib sheet for what the differences are. The mode is just the most frequent value. You think of it as the most popular. It can be used on any kind of data, nominal, ordinal, interval ratio. The disadvantage of it here is that it's kind of crude. It's a very crude measure of what the most, what central tendency looks like in a data set. Then you got the median, which is literally the middle value. It really only takes that you put the numbers in order to really be able to, you know, to look at the median. Think of this as sort of the middle child. It's just, it's, you know, it's literally just dead center where you have half the data above, half the data below. It doesn't really make any sense to use a median on nominal data, right? So that's why you don't see nominal data listed here. In order to put things in order and find a middle, it's got to be at least ordinal and then interval ratio as well. The disadvantage here is it only uses 2 points at most. For many data sets, it's just going to utilize 1 point of the data, but in other cases, it'll use 2 points because it'll actually find the midpoint between the two center values. But at most, it's going to use 2 data sets. So if I have 1,000 data points, I spent all this time collecting all this data to find the median, I'm going to ignore most, if not all of it, except for the middle 1 or middle 2 numbers, which is sort of a strange thing. The other numbers don't matter; they're just placeholders. Then you get the mean, which again is the arithmetic average. So you can think it's the one that's super mathy, right? The one that requires an equation to sort of figure out. Because of that, it actually doesn't really make any sense to use the mean on ordinal data. So again, go back to the runners in a race example. You got something that comes in first, you got something that comes in second, third, fourth, fifth. You got all these orders, right? Fifth, sixth, seventh, all the way through. It doesn't make any sense to add up all the places in a race and divide by the number of places to get an average place. It's sort of a weird thing. We don't typically use it with ordinal data. So most of the time the mean applies to things that are interval or ratio. Right? The only disadvantage here is that it's affected by skewness or outliers. Extreme scores, very large scores on either end, can actually pull the mean up or pull it down, and that's actually a concern a lot of times when using the mean. How do you find the mode? Well, one mode, two modes, red mode, blue mode. Right? So it's not that hard. Modes are, again, it's crude, it's very quick and easy to figure out. Just point at it. There it is. All right, so you just figure out what values are the most frequent. That's it. Okay. Problems with the mode. There are multiple modes, especially with group data. The mode becomes sort of not very useful. If the mode is supposed to tell us what the most common or likely person is like, and there's multiple common most likelies, it starts to lose its luster a little bit. It doesn't really tell us really any information that's really very good. The mode is overly sensitive to things like the size and number of class intervals. Different intervals equals different modes. And we saw that in the last lecture where when we used a ungrouped distribution, we had two equal modes. And then when we regrouped them, all of a sudden there was one overwhelming mode and then another mode that was sort of much smaller. So changing the size of the class intervals or the number of intervals you use can affect which class becomes the modal class. Okay, so it's not a very dependable population estimate either. So because it's going to change quite often, or at least to some degree from sample to sample, it's not very good by itself as a measure of central tendency in the population. The median, again, this says the middle child. I don't know, this is probably too old for many of you, but I don't know if anybody's watched the Brady Bunch. There's always this complaining by it actually goes right into it. I forget her name. Jan, pretty sure. Jan, the middle child. It's like, Happy Middle Child Day. Oh, you didn't notice it was Middle Child Day? Of course not. No one ever does. We're sort of middle children. There's a tendency, or at least a stereotype about them being sort of the forgotten, or the child who has to sort of fight for the most attention and things in a family. But so the median is the points at the exact the middle of the distribution is the 50th percentile, right? It is literally has half the data above it, half the data below it. It is less sensitive to issues that the mode has, like if you change the number of class intervals and that kind of stuff. It doesn't really affect the median very much. It's more useful for inferences. It has a better connection to the population, so it's actually much better than the mode in that sense. It ignores all but the middle values, right? So it's not very affected by skewness or outliers, because if you have one extremely high score on one side, well, we're going to ignore it anyway and just use the middle values. So it doesn't really matter. So this in the bottom, research fun fact. 93. This is a little bit old. It's old, but I think it still holds. 93% of American respondents, compared to 69% of Swedish respondents, believe they were above the median in terms of driving ability. So the median is a 50th percentile. So if you're at the median, that means that 50% of drivers are above you, 50% are below you. So somehow 93% think that they're in the upper 50%. So we tend to overestimate our driving ability, amongst other things, where even though Swedish participants also overestimated, they did so at a much lower degree of overestimation. Okay. Again, stop me if you have questions. Let me know if anything you want me to clarify. All right. So the median. So how do we find it? It's actually fairly simple. So if I want to find the median in a set of scores like this, the first part's going to be, well, I need to order it. So what's the smallest number here? It's like 2, 2, 3, 4, 5, 7, 8, 9, I think. I get that right? I don't know if you guys are still with me or not. You two gals, Mary and Haley. I think I got that. 2, 3, 4, 5, 7, 8, 9. So if this is our data put in order, yeah, okay, that data put in order, then what's the median? It's very simple. This one, yeah, it's just the number right in the middle. I got 3 numbers above, 3 numbers below. Super easy to find, right? This ignores most of the data set and just looks at the middle number. So let's look at the second one. So if I want to order it, the smallest looks like 5. 5 and 7, 9, 10, 11, 12, 13, and 15. I think that's it. So what about now? So now that I have an even number, 2, 4, 6, 8, I can't just find the middle number in an odd number data set like that. I need to look at the 2 middle numbers and just ask, okay, what numbers in between or in the middle of those 2 numbers? You can add them up, divide by 2 if you like to find the midpoint, and just figure out that the midpoint is 10.5. So if there's an odd number, you literally just grab the middle number. If it's an even number, then you find the middle 2 numbers, find the midpoint between them, and that's your median. What happens if the 2 middle numbers, let's say the 2 middle numbers happen to be 11? 11, 11. Well, then the median's 11. All right, so if the 2 middle numbers you find happen to be the same number repeated, then you don't need to find the midpoint or anything. It's basically just that number. Okay. So it only matters if the 2 middle numbers are different numbers. You now need to find the midpoint of the 2 numbers to figure out the median. All right. Easy enough. Median is easy. Mode is easy. And so figure out the mean's not difficult either. It's just more work. It's not quite as easy as just pointing at a graph and saying there it is, or you know, putting data in the order like this and then saying, look, it's the middle one. Those 2 are super easy in looking at the central tendency. The median, well, not complicated. It just requires you to do more. Okay. So the mean, you may see it in some places with anytime you see a bar like this over a variable. So if x is a variable and you put a bar over x, it's telling you that's to find the mean of that variable, which is why the cartoon back here is sort of referring to this one. It says like maybe you set your bar too high, meaning the bar over x, because that actually indicates mean. That's why that joke is there. I think in the textbook that's that's in the syllabus, that sort of online textbook, they use m of x, which is fine and it makes sense. Anytime you see m, you use the mean, and the mean of x in this case. It really just says this sigma, this Greek letter sigma, is used for sum. Take all values of x, all individual scores I in the variable x, and I want to sum all of them from the first one, I equals 1, through the nth one, which is the last one. Right? If I have 30 values in a variable, so n equals 30, so I'm going to sum xi from I equals 1 all the way through 30. So that's what that says. That's why it's written that way. So we're going to sum up all the values, and then I'm going to divide by the number of values. So again, if I have 30, I'm going to sum up all 30 scores. I'm going to divide by the number 30, and it's going to give me an arithmetic or mathematical average of all those points. We like it because it's an unbiased estimate of the population mean. And unbiased is just a fancy way of saying that every time we take a sample, sometimes the mean is overestimated, sometimes it's underestimated. But in the long run, it's about equally high and low in terms of estimates, and it gives us an unbiased sort of estimate of the population. The sample mean is usually referred to as M, and this is the lowercase mu, mu, from as a Greek letter, and that we usually use to refer to the mean of the population. So I just said, like, oh my God, it's our first equation. It's really literally the first equation that we sort of talked about. So we managed to get through the whole first day and a lot of the second day before we even got to an equation. So that's pretty cool. Here we are, first equation. Congratulations. Okay. This is like one of my favorite jokes. Statistics, the discipline that proves that the average human has one testicle. So this is, again, the issues with statistics and how it gets used sometimes can be a little ridiculous and a little bit sort of goofy, like that the average American family has 2.5 kids. I always wonder what a 0.5 kid was. But anyway, so here, if we're looking at trying to figure out the average, right, we want to find the mean of X or the X bar or whatever it is. It's, again, not difficult. It only becomes a pain in the butt when you get more scores. So this is really just going to be 3 plus 4 plus 6 plus 10. So that's 10. That's 10 is 23. So we got 23 divided by 4. So what is 23 divided by 4? Can't think of that off the top of my head. $23 divided by 4 equals 5.75. 5.75. And that's our mean. That's it. Of the data set that has 3, 4, 6, and 10, the average value is 5.7. Simple, simple. Okay? All right. Moving on. So the downside, so this is actually funny, this was actually in 2018, so, it wasn't too long after sort of Trump had already started sort of in the thing. So I asked this question about, what do how do you rate Trump's presidency? And the issue here is that, like, the majority of the class was sort of down at the bottom. This is not surprising for the number of reasons. This is not meant to be a political debate. I just was asking because it was sort of a hot topic at the time what people thought, because I knew you would have this sort of strange thing. And the scores were, I think, rated 1 to 10. Okay, so how do you think he's doing on a scale of 1 to 10? So most folks fell into sort of 1 to 2. So of them, there looks like about 37 people said something like 1 or 2. There's a couple 2s and 3s, a couple 3s and 4s, 4s and 5s, maybe just 1 even. 1, 3, 2, 3, 1, 3, 4, 1, 4, 5. All the way up to one person that rated him as a 9 or a 10, something at the top there. So I sort of made this into a histogram. So I made these sort of small classes. So up here is one person. So the goofy part is, even though the reason why I put this down as the downside, the skewness and outliers, is that even though the mean of this data is going to be mostly driven by this large number of frequencies on this side, what's going to happen is these trailing sort of skewed values, like this one, is actually going to work because it's so different, than the rest of them. It's actually going to work to pull the mean up to look like overall the class actually has a higher rating of the presidency. This is again in 2018 than he actually had because of a single or a few extreme scores that are going to pull it and make it look more positive than it really is. And if I were to do the median here, because of the number of scores, the median is still going to be in this thing. So the median is actually going to reflect this large category here better than the mean would because of the skewness and the high scores on the right-hand side. All right, so skewness can cause a problem, or outliers. So these scores are disconnected from the rest. They're sort of outlying. They're different scores from everybody else. Now, if I had asked this question, a different part of the country, or some, I don't know, a Trump rally or something like that, then everybody would be piled up on this side with, some going the other direction. It just happened to be that, this was in 2018 on this is at CSUN, which is a large, very diverse campus, in the San Fernando Valley. You can get very different responses than if you were someplace back east or in the South or in the Midwest or whatever. You may get a lot more variability and a lot more stuff for people in the middle at other places. Just happens to reflect what the opinions were like of this particular class in the spring of 2018. Anyway, so let's talk about the influence of outliers and how outliers can be problematic, and what outliers can do to the mean, where it doesn't really seem to affect the mean or the mode or the median very much. So let's look at this data set. So the data set is 8, 10, 9, 9, 6, 6, 9, 13, 10, 9. When it's out of order, and it's very sort of hard to figure out what's going on. So if we actually put the data into order, right, so here's the first ordered data, it actually becomes pretty easy to figure out the first two. The mode and median becomes sort of, they jump out at you pretty quickly. Or the mode here is 9, because there are 4 9s, only 2 10s, 2 6s, so 9 is the mode. And also, if you look at, there's 2, 4, 6, 8, 10 scores. The two middle scores are 9 and 9. All right, with 4 above, 4 below, or if you want to think of order in terms of numbers, 4 below and 4 above numerically. So this 9 and 9 are the two middle numbers. Because they're the same number twice, I don't really have to do anything. I just know that the median is also 9. Pretty straightforward. For the mean, well, I need to add these up. So, okay, 6 plus 6 plus 6 plus 8. I got 4 9s plus 9 plus 9 plus 9 plus 9. 2 10s plus 10 plus 10 plus 13 equals. So the sum, if I were to sum up all these, again, remembering our mean, the sum of xi up here over n, I get 89 over, and I have 10 scores, so 10, which means that the mean is going to be 8.9. Okay, I think I did that correctly. If I didn't, please let me know. So our mode, median, and mean are all pretty close together. 9, 9, 8.9. I mean, yeah, I know the mean's not exactly 9, but that's pretty close. 9, 9, 8.9. So this is looking, somewhat symmetric. It's got one mode. It's looking for, pretty good. It's maybe a normal distribution. Now, what happens if we change just one number? So all I did here was I took the same data set. I just replaced one number. I replaced the 13 here with a 33. Okay, so I took what was the highest number before and I just made it higher. I made it more disconnected. Okay, so if we put the data in order, it comes out that everything's the same, except we get one number that changes, this 33. So if again, we look at the most frequent number, still 9. The number in the middle, right, is still these two 9s. Right, so the median ends up being still 9. But now what about the mean? So you can either add up all the numbers back up again, which is fine. But if I take 89, subtract 13, and add back 33, I get the same process. I'm just sort of cheating a little bit. So that ends up being 109 over 10, which gives me 10.9. All right, so just changing one score, 10.9, I go from 8.9 to 10.9 by just changing one value in the data set. Right? So it's pulling the mean away from the mode and the median, which becomes a fairly common thread, a thing that you can think of when it comes to the mean, the median, and the mode, that if the mean, median, and mode are all about the same like this, that means the data is likely very symmetric. If the mean is larger than the median, mainly the median, but the mode and the median is larger than the median, that means there's likely positive skewness. We have, or are high positive outliers. If the mean is lower than the median, that means you're having large negative outliers, or large outliers on the small end that's going to pull it away from the median on the lower side. So again, we have positively skewed distribution. The skewness, right, is going to pull the mean up away from the median and the mode. So this gap, when the mean is larger than the median, tells you that there is positive skewness. And the same is true on the flip side. That if the mean is lower than the mean, it's likely there's outliers or negative skewness pulling the mean towards those large values and causing a gap between the mean and the median and mode. So when a distribution is symmetric, you should expect the mode, the median, and mean all to sort of equal one another. It says mode 1. If you have one mode and it equals the median and the mean, then the distribution is likely symmetric. It's when the mean starts to pull away from the other two that it can give you information about outliers on one side or skewness going in a positive or negative direction. Okay. So again, if the mean is larger than the median, positive skewness. If the median is larger than the mean, meaning that the mean is smaller than the median, that's likely means that there's negative skewness. Again, the mean is larger than the median. Right. The mean gets pulled up away from the median. That means you got positive skewness, or at least some large positive outliers. The same thing's true the other way around. Right. That if it's skewed this way, your mean is going to be pulled away from your median, okay, towards the lower end.